All right, spotlighted. Hello, everyone.
André.
Hey, is it okay to share my screen here?
Yes, yes, you can try it.
Let's give that a try. I think it should be this one. And give me one moment. Can you see everything now?
Uh, yes, but can we want to increase the volume in the room?
Okay.
Just wait a second. Yeah, now I'll introduce.
Okay. You tell me when.
Okay, yeah, now it's very loud.
Sorry.
So no, yeah, it's on our side here in our room. So okay. So yeah, welcome back, everybody, to our workshop. I hope you enjoy coffee and cookies downstairs. For those of you who are here, there are actually still some cookies left downstairs, I think. So now for the next two talks, we go to North America. So that's very exciting. And so we're going to jump halfway across the world and land in just outside of Chicago at Urbana-Ch. So our next speaker is André Schleife, and he is a Blue Waters Associate Professor of Material Science and Engineering. He obtained his bachelor degree and master's, the diploma and the PhD in Jena at the Friedrich Schiller University. And then after that, he did a postdoc in the United States at Lawrence Livermore National Lab. And then after that, then he moved to and became a professor at UIUC. He's received a number of awards, which you can read in his biography. And he will share with us today his work on triggering ion dynamics in materials by laser and particle radiation.
Okay, great. Thank you so much for the introduction and the opportunity to present at this great workshop. I would have preferred the cookies instead of being just in my office, but instead, well, that's what the world is these days. And what I did enjoy though was the previous presentations. I'm looking forward to the following ones. It's great to be part of this workshop. And over the next, say, 45 minutes, I will take your time to discuss my group's work, my group's computational work, and how it connects to materials design, which is the topic of this workshop. So maybe I start with the big picture, which is that in my group we use advanced computational techniques, first principles techniques, to predict materials properties, to connect them to experiments, and maybe eventually achieve either materials design or maybe materials selection. So I'll give you some examples of frameworks, computational frameworks that we use to describe such properties, and I will also show you their limitations. I think I'll put an emphasis on that and see where further improvement is needed. Examples in terms of materials, you will see examples from electronic materials and maybe energy applications, and as well as antiferromagnets and materials with defects, and maybe how we can make them usable for quantum computing. Before I jump into all the technical details, I want to show you a kind of crowded slide that acknowledges both the people who do the work. Okay, so here are the students whose results you will be seeing today. I mean, partly, we're not going to do a large number of, of figures per student, but all of these people have tremendously contributed to what you'll be seeing today. And then, of course, funding agencies, right? So Sandia National Labs, the Office of Naval Research, NSF, have contributed to our work here. The DFG has actually contributed to a Mercado Fellowship with the SFB 1242, which allowed me to stay in Duisburg for 2 months this summer, which was very a nice change after not traveling at all for so long. And then I also want to point out the Joint Lab for Extreme Scale Computing, which is really, you can see the logos here, is a sort of like a group of big computing centers that work together, and with them we are able to improve the implementation of our codes on massively parallel supercomputers. I'll point this out briefly later in the talk. Okay, so the topic of this workshop, right, so it has transformational materials in the title, made me think a little bit about, well, what materials are truly transformational, right? And many in the room over there or on Zoom either already believe it or have experienced it firsthand in their research, that a lot of challenges of global societal dimension can potentially benefit from better materials, from more advanced materials. And that's where transformational would come in. So the figure you see here, you don't have to look at in detail. It's just an illustration for climate change, essentially, which is one of the examples over here. Other examples include how we make and how we store energy, health and medicine, transportation, food and water. All of these problems require advanced materials. Or so we asked ourselves, because one of the back of the envelope calculations I want to give you, especially relating to climate change, is if you're doing computational research and you run on a standard node in a standard supercomputer, that will take you typically 1 kilowatt hour of electricity for each hour that you run that node. Okay, it takes you another kilowatt of electricity to cool the computer to a useful temperature. So 1 node hour takes you 2 kilowatt hours of electricity. If you compute that, if you convert that to CO2 production, that means 1 node hour produces about 1 kilogram of CO2. Now, that, I don't know if that means much to you, but to put it in perspective, flying from Chicago to the West Coast in the United States is about 250 kilogram of CO2 per person. Okay, flying to Europe is maybe 2 tons of CO2, or in other words, flying to the West Coast is 250 node hours of simulation time. So it does make some sense to think about where can material science really be most transformational versus maybe this has become really more like an engineering problem or a policy problem, because that is definitely true in some of these climate change related questions. And so I will not give you the answer how to find the most promising material to study or anything like that, but I will show you at least one approach where I think data science and databases that we have nowadays can really help to not answer that question so much, but maybe to point you in the right direction. And so what we did last summer during the height of the COVID pandemic here, we worked with a couple of undergrad students. We looked at various models for figures of merit, right? So in this case, for instance, maybe the power conversion efficiency of such a solar cell system, let's say. We came up with simple figure of merit models, and the simplicity was key because we then used existing materials databases and ran that figure of merit calculation simply for all materials in the database. Not because we thought, oh, maybe by this we find a material that works much better all of a sudden, but to answer one question, which is where are we with what's currently used with respect to what is possible? And so we simply did this figure of merit calculation, we histogrammed that, and then you can put that in relation. Now again, I said it earlier, I'm not going to give you the final answer to what is now most promising. I don't think we have that answer, but I'm trying to encourage you to make use of these databases in such a context, maybe to kind of determine what is possible in an ideal world and then how close can we get until we have to overcome maybe a certain physics paradigm dictated by the figure of merit assumption that you made in the first place. Okay, so transformational materials is maybe a difficult question to answer, but what I do want to point out are 2 transformational developments that have happened and are happening in material science. And I think they will then influence the remainder of my talk. One is that nowadays we can do experiments with, so not we in my group, but people in research can do experiments with incredible spatial and temporal resolution. So we have atomic resolution at atto to femtosecond timescales. So that gives an incredible amount of experimental detail, and it allows an incredible amount of fundamental understanding. It also brings challenges, right? So it produces massive amounts of data. It really points out this multi-scale problem. If you measure something on an atto or femtosecond timescale, you cannot easily go to nano or microseconds. So there is a multi-scale aspect to it. And that is true both in experiment and theory. So the picture up here is an experiment I found in literature. It's a recent publication where people measured momentum maps of frontier orbitals. The bottom right shows a movie that we did from a simulation that we did in my group, where we expose, in this case, a piece of aluminum to proton irradiation. But the timescale that you see here is femtoseconds. Okay, so that's maybe the first transformational development. So we need models and theory that can cope with that, right? Incredible spatial and temporal information. The second one comes out very nicely. If you look even at the agenda of this workshop, you can see it, is nowadays data and code both become more and more freely available and more accessible. So what I did here is I took a screenshot, I think I did this earlier this year, of the website of the Nomad repository, which is a website where you can store and upload, users can upload data sets from, in this case, total energy calculations, for instance. And again, we don't have to look at the details so much, but my point is that this website, at that time when I took the screenshot, provided 50 million total energy calculations, okay, for free to download. So that allows a whole new type of doing research, right? It allows unprecedented ways to do uncertainty quantification, for instance, without running new simulations. And then the second part of the screenshot actually points to the second point I want to make, which is why I left it on here, is Nomad is not the only repository. We have people here, and probably in the audience or as speakers, that work on their own or that have used many others. Materials Project is one example. There are many of them. So that is a huge opportunity, and I think that's a new transformational development in material science. In this talk, I will not discuss it too much in detail. I will focus maybe more on the first one, but nowadays I think it is possible that you can perform research using those databases without running too many simulations yourself. So one example we looked at in the past is where we looked at heterojunction design for semiconductor heterojunctions. So I should say design of semiconductor heterojunctions. In this case, we used actually Materials Project. Okay, with that, I'm now trying to come more closely to the work that we do in my group and where we do develop frameworks further. And one big topic, I said it earlier on, is related to excited states. So one of the core research activities in my group revolves around excited states. And so I will show you how we can nowadays obtain a very accurate description of optical properties and then learn something about the structure of materials. So that's one of the examples that we've used this for. And by structure here, I mean both crystal structure as well as magnetic structure. So the magnetic configuration of the material. So just to walk you through the slide, on the top left, you can see an image that used our first principles data. So the image is computer generated, but it used our simulated data for sulfur doped titanium oxide. And as you go from maybe this kind of like almost like whitish looking object here, the sphere, you go to darker and darker. What happened is we increase the amount of sulfur doping in the titanium oxide, and you can see how that affects the optical properties. So in other words, we have a very accurate description that we can obtain with our techniques. And then we use that. I will not walk you through tons of examples because I think that at some point gets boring. I will show you some briefly, and then I'll discuss the limitations of the framework and what we need to do. So one example that we have started to look at is the connection of optical properties and crystal structure. And in this case, you see the system here is cadmium selenide. And that is a collaboration with Andrew Smith here. He's a faculty member in bioengineering on campus here at UIUC. And he makes nanocrystals of this material in his lab. So he synthesizes them, and his question was whether it's possible to distinguish that material in its zinc blende structure from its woodside structure purely based on spectroscopy. The reason is that these nanocrystalline samples are not so compatible with high or ultra high vacuum techniques or an X-ray diffraction, and so if he has a spectroscopic approach to distinguishing these two crystal structures, that would tremendously benefit his research. In this case, what we show here in this figure is bulk simulations for the material. We also performed the simulations for nanocrystals, and we found indeed that while the absorption onset does not tell these two crystal structures apart, let's say for instance comparing the red and the green curve here, at higher energies there are characteristic peaks that correlate with specific crystal structure. And then the second example is we did a similar study for magnetic ordering, in this case of a material manganese 3 tin, which you can sort of see on the right hand side here can appear in various magnetic orderings, but at very low temperatures. Apparently the people report a spin glass phase. We did that sounds complicated, and it is complicated for simulations. So we started with the sort of phase that appears at slightly higher temperatures, which is a non-collinear antiferromagnetic phase. And then at even higher temperatures, you see a phase transition to a different non-collinear antiferromagnetic phase. And we computed optical, in this case, magneto-optical properties, actually, Carrier rotation, and wanted to see if we can tell these different phases apart. And it turns out that for the different antiferromagnetic phases, that's not so easy because typically the signatures are not so strong. If you were to make this material ferromagnetic, the signature is much larger. So point being, again, that we can use the interesting physics of the excited electronic states, such as exciton and screening or magneto-optical effects, and can learn something about materials that are applied, for instance, as photovoltaics, which was discussed before, or optoelectronics, or in this case, the nanocrystals are used for bioimaging. Okay, so which framework we used? I'll have to briefly show you some equations to point you to the limitations. So typically when we calculate optical properties, what we use is a three-step procedure where we calculate first the crystal structure of a material. I'm just using this example here for illustration purposes. You will see one result later on for this material, which is methyl ammonium lead iodide. We obtain the crystal structure from density functional theory, and then we feed that into what is called many-body perturbation theory. So in this case, within the GW approximation for the self-energy. So for those of you in the field, you know this, of course. It's not our technique, it's a standard technique in the literature. For those of you who are not in the field, think of this GW approximation as a way to describe the electron-electron interaction more accurately than DFT does. And it does so by incorporating a screened Coulomb potential here. That'll be important in a moment. And once we know the electronic structure with good accuracy, we then calculate the optical properties, and that also happens within many-body perturbation theory. In this case, we have to look at now two-particle excitation. I mean, people discussed this framework before. We have to look at a two-particle excitation. That means we solve this Bethe-Sapir equation for the optical polarization function, which is given here. And then we can relate that to a dielectric function, which is what people measure, for instance, in ellipsometry. So that dielectric function here is sort of our target. The reason I'm showing you this is the following. The way this equation actually is solved is it is rewritten into an exciton Hamiltonian, and we don't need to look at the details of the Hamiltonian unless you have specific questions. But this W term here that I mentioned also for the GW approximation is again the screen-Coulomb interaction, and that is exactly what we think is critical. Christian in his talk discussed very nicely how screening can either screw up or improve or tune your optical properties and excitonic effects and things like that. So I'll come back to that in a moment. So this is the framework we used, and this is also the point where I want to mention this collaboration with Jülich through the Joint Lab for Extreme Scale Computing, because we worked with Eduardo Di Napoli there and his team on getting the solution of this Bethe-Sapir equation implemented on massively parallel computers and also on GPUs. So he helped us with that. Okay, now, after you saw, okay, we can do optics and maybe we can even connect it to the crystal structures, what are the limitations of the approach? And I'm pointing you to those because that's, I think, where future development is either needed or promising. And I'm just recapping the most important equations here. One is this GW approximation, one is this exciton Hamiltonian. Both include the W term, and the W term specifically is the Coulomb potential now screened by your material being present. Right? So in a bulk material, you would have to describe screening due to that material. As Christian said, near a surface, you may have very inhomogeneous screening because, in plane and out of plane, the screening is different and so on. So epsilon is a tricky quantity. I will not go over low-dimensional systems because Christian discussed this. We looked at nanotubes. We didn't look at 2D materials too much, but we looked at nanotubes as well as the strain influence on those, and screening matters for that, as we saw in the previous talk. What I do want to show you is developments in terms of materials with large lattice polarizability. So the fundamental assumption or the fundamental approximation that many people do when they perform these simulations here of the Bethe-Sapir Hamiltonian, they use a so-called static approximation to the screening, which means that this screening term, which is in reality is position and time dependent or wave vector and frequency dependent if you Fourier transform, they make an approximation that the dependence on the frequency goes away. And we believe that we have indications that this is a problem potentially in materials with large lattice polarizability, simply because the lattice can also respond, but at a different time scale than the electrons. And so if you neglect that time dependence, you're kind of losing that information. Anyway, I'll show you that in a moment. Before we go there, I want to point you to another example where screening is critical, or more precisely, where the description of screening is potentially challenging, and those are doped materials. So if you have a semiconductor, so for instance, methyl ammonia lead iodide, and you dope this material, let's say we n-dope it, meaning we introduce free electrons in the material. Those free electrons can also respond to an external electric field. And so in this response function picture that Frank really nicely described earlier today, that response of the free electrons has to be taken into account, because this dielectric screening, or this dielectric tensor here, is nothing else other than a response function. And if the electrons due to doping affect the response, it would have to be taken into account in the modeling of the screening. And so we did this a couple of years ago for zinc oxide. Here I want to show you some data briefly for methyl ammonia lead iodide, where we actually calculated the exciton binding energy using this framework and accounting for different electron doping concentrations. So that's actually the x-axis here on the plot, right? So the doping concentration, and then we calculate exciton binding energies in this material, simply because, for photovoltaics, the exciton binding energy is relevant if you're thinking about separating the electron in the hole after you created it. Then too high binding energies are not so good, and too low binding energies may be preferred. And so the question is, what is the exciton binding energy? And in that material, so I will just come back to basically to the bottom line. That Josh published more details in this paper. But if you're looking at this material, if you're looking at highly pure crystals of this material, in other words, very low doping concentration, very low unintentional doping concentrations. Exciton binding energies would be higher. So that's what the numbers here come from our predictions. If you look at maybe precursor mismatch samples that are also reported in the literature, maybe there are more defects present. So in other words, there is unintentional doping and you see lower binding energies. And indeed, if you look at the literature, you do see that the range of binding energies that's reported for this material is large. And we believe that effects because of this and then the corresponding unintentional doping can at least explain this behavior in part. Okay, so with that, let me come to this dynamics problem. And I will show you one more slide with equations, which is this one. Earlier I said, typically when you solve this Bethe-Salpeter Hamiltonian, you assume that this screened Coulomb interaction is frequency independent. Now, you can think about examples where that would not be fulfilled, right? One may be electronic screening, like purely effects due to electronic dynamics. That is typically believed to be small simply because the Plassmann resonance in a material is typically much higher than the exciton binding energy, and so the remaining dynamics in the low energy range of the exciton binding energies is not so big. But we do believe that in a material with a large lattice polarizability, there could be a contribution due to phonons. So Frank also talked about the electron-phonon interaction. That would be what needs to be taken into account here, right? So the effect that electrons, that phonons can also contribute to an external electric field. Now, that makes this frequency dependent, right? The response itself can be frequency dependent, but then if you have two mechanisms for screening that appear in different frequency regimes, that in itself would make this whole screening term frequency dependent. Okay, so what we use now to incorporate into the Bethe-Salpeter approach is Shindo's approximation. That's again known in the literature for many years, and we express the model function for a dynamically lattice screen Coulomb interaction using a Fröhlich model. So that's what you can see here. That's the final expression that we then implemented. Once this is frequency dependent, it's not sufficient to diagonalize only one excitonic Hamiltonian anymore, but now you have you need to diagonalize multiple, and you need to find the excitation energies that fulfill this relation simply because of this frequency dependence. Okay, let me show you the application. So far, so this is work in progress. So what I can show you so far is an application to bulk materials, to bulk, in this case, insulator, so magnesium oxide. And what we calculated here is the dielectric function, the imaginary part of the dielectric function. I said earlier that's a quantity that people can measure in, let's say, for instance, ellipsometry. Experimental data is shown in magenta here. The data without excitons, we don't need to look at too much here for this material. The difference is very large, and that's well understood. What is more interesting is that if we were to screen the exciton, the electron-electron interaction statically electronically, we get the red curve. So that's also actually that's old data that we published a couple of years ago. If you screen with a complete static lattice contribution, you get this blue curve, and you can see how the lattice, if you use the static lattice screening, which we know is not correct, right? It overestimates the effect, but you can see the range between which you can tune this interaction, or between which we have to pick from using the first principles implementation. And then what we did, what Josh and Zhao did, actually, it's unfortunately not published in a journal yet. We're working on that. It's in their PhD thesis. Is if we implement a dynamical screening and we then compute the optical spectrum, we see an improvement in terms of the peak position and the peak height. So it kind of improves the agreement with the experiment here at the onset. We also see effects at higher energies that seem to push it in the right direction compared to experiment. And then the last caveat I want to say here is that these are effects that we really want to now explore in a material where the LO, the longitudinal optical phonon frequency, is either on the same order or maybe slightly larger than the exciton binding energy, such as aluminum nitride or gallium nitride. In those materials, the effect is expected to be very strong. Okay, I'll leave it at that. So I think this dynamical screening is something we need to include in the Bethe-Salpeter approach. But in the interest of time, I want to show you another aspect that we looked at for these optical properties before I come to the laser interaction that's in the title of my talk. So if you look at this framework and you just take a step back and say, okay, if I do the experiment, I come in with my laser pulse, right, or a light pulse that excites the electrons. What happens is the electrons go from a ground state into an initial non-equilibrium electron-hole energy distribution. Okay, that's your initial excitation. That's what we described using the picture that I just showed you, right? This Bethe-Salpeter approach. However, that's just the starting point of a whole cascade of processes that then follow in the material. This, you can see this in this cartoon picture. These electrons are not equilibrium at all, there's not even a temperature in the early stages, they will relax, right? So there is electron-electron scattering, there's electron-phonon scattering, that brings them first, usually they're different in timescales, and usually what happens is that these electrons first become a Fermi distribution, the holes become a Fermi distribution with a temperature, and eventually it will also recombine. So this time dependence, we would like to describe, and we would like to describe it because people access it in experiment, right? So pump-probe techniques are ways where you vary the time delay between this initial laser pump that creates the excitation, and then the following probe pump that probes the properties, you know, at certain time steps. And to describe those experiments, we have to go beyond what I just told you. Specifically here, we worked with Marius Grundmann's group in Leipzig because they can do time-resolved ellipsometry. And in that case, they looked at zinc oxide, which, you know, maybe as a material has now been studied for a long time, but in their case, they used this because it is a very well understood material. And if you apply a new experimental technique like this time-resolved ellipsometry to it, it's nice to have some reference data to compare to. And their pump pulse created these excited carrier distributions. Okay, you can see here, excited electrons, kind of Fermi-like, excited holes, also Fermi-like, after 300 femtoseconds. Okay. What that looks like in the band structure is the following. These excited electrons occupy lowest conduction band states, of course, especially, you know, you see the distribution here actually. And what that leads to is an effect called Bernstein-Noss shift. So meaning transitions from the valence states into those lowest states cannot happen anymore because the final state is occupied. So that needs to be taken into account. The second effect is a band gap reduction, which also occurs due to the occupation of these conduction band states. And then you get transitions. These are two sets of transitions. One is indicated down here, which are transitions within the valence bands, because you know you emptied up those states, so you can now get transitions, and you get transitions in the conduction band states from these lowest occupied ones into higher ones. Those contributions need to be all accounted for if you're looking at, you know, time-resolved studies. So the way we approximated this now in our framework is we treated most of these effects, and that's again a limitation of the current framework. Most of these effects in DFT. So all valence conduction band transitions as a function of carrier concentration and temperature we treated within DFT. We also treated valence-valence and conduction band transitions within DFT. Mostly because in the Bethe-Salpeter approach, we currently have an implementation that can approximately account for free electrons, but not for temperature. So I'll tell you that on the next slide. And then we assumed, that's the other limitation of the approach, we assumed electron and hole temperatures extracted from experiment. Ideally, we would like to predict those. So the excitation density, that depends on the pump pulse. So that is, I think, okay to take from experiment because it depends again on what they shine on their sample. But the time scale of obtaining these temperatures and the value of the temperature, that would be something we would like to predict. Okay, now excitonic effects are important, and so what we did here is we simply accounted for excitonic effects at 0 Kelvin, again, because we currently cannot study temperature, but taking into account the free electron concentration in a similar way as we did for the doped material when I talked about methyl ammonium iodide. So we use a Thomas Fermi model, we implement the extra screening, and then we solve the Bethe-Salpeter Hamiltonian. Let me just jump to the results in the interest of time, which is a comparison here now between so that's the delta epsilon, so that's how much the imaginary part of epsilon changes as a function of energy at a certain time, for a certain pump probe delay. And the black curve is experiment, the red curve is what we computed from our simulation. And you can see that, you know, the overall structure of the curve comes out very well in our simulations after we incorporate the effects that I discussed in the previous slide. Right? So I think that incorporating such a description is critical and allows us again to describe these experiments even in the time domain. That data is in this paper. We also looked at methyl ammonium iodide. I think that's not quite through peer review yet. Okay, at this point I want to stick with time dependence, but connect now the effect of electronic excitations to ion dynamics, because I think we have evidence, especially in our simulations, but I think also in the experimental literature, that these excited electronic states are not just there and affect the electronic system, but they can influence how ions move in the material. So maybe the example that comes to mind first is radiation hardness of materials, right? If you have a piece of, in this case, silicon, and you expose that to energetic ion beams, which is of course what people do in the lab to understand the material properties, the material will experience defect creation, and any excited electron states that affect the creation of these defects will be important for this material. I will not discuss this example here in detail. In the literature, you find examples where people try to do that for two-dimensional materials. So this is not our data here, this is a paper from the literature, but I use this here as motivation. So what happens if we expose materials to either swift heavy ions or highly charged ions? And so I'll start with our example here where we used bulk magnesium oxide. The interesting physics here is you're really either probing or simulating or experiencing non-adiabatic electron-ion dynamics. And what we want to use it for eventually, that goes to the title of my talk, we want to use it to modify materials, modify the defect properties of materials, maybe even all the way to create specific defect properties in a material that is suitable to be used for qubits. All right, so the framework that I use here must be extremely well known in Halle, of course, is time-dependent density functional theory. In our case, we use the real-time time-dependent DFT, where we propagate these time-dependent quantum equations in time. Okay, so we use a numerical integration scheme to propagate the time-dependent quantum equations in real time. That allows us to account for external potentials that are time-dependent. Specifically, in the example that you will see first, is that it will be a moving ion. The second example, it will be an external electric field. We implemented that into the QBox/QBall code. So these are both two flavors of the same code. It's a plane wave DFT code, massively parallel, and it allows us to run these time-dependent simulations. I also should point out a collaboration with the Joint Lab for Extreme Scale Computing, in this case with Argonne National Lab, where people help us to maybe come up with better numerical integration schemes. I will have no time to show you that data. But let me explain what happens in the material. So what we looked at is magnesium oxide. Okay, so you can see the bulk magnesium oxide cell here. It's also here in the background of this figure, you can see the atoms again. And we're looking at a situation where this material has an oxygen vacancy defect, right? This blue bubble here is actually the electron density, the partial electron charge, the partial electronic density associated with the defect state in this material. This is the same bubble essentially that you see here in the background of this figure. If you don't like this real space representation, you can look at the energy, of these states. You see in this material you have a valence band maximum of magnesium oxide and a conduction band minimum, and then somewhere close to the middle of the band gap is this defect state, which in its ground state is occupied. Okay, so now we start our time-dependent simulation where we shoot a proton on this black arrow through the material near the vacancy. Okay, and we plot as a function of time the occupation number of this defect level. So how does that change as the proton moves past this defect? And what we see is that this process depends very much on the velocity of the proton. Okay, slow protons, yeah, they do something at first, but then that effect essentially goes away again. And after the proton is gone, the vacancy is still occupied with 2 electrons. Same is true for fast electrons. Okay, for fast protons. They move past the defect, but they don't change the occupation number much. However, there is a range of velocities, and this actually correlates with the energy distance of the excitation that happens in the material, at which you can very efficiently excite the defect state. And so the first thing we did is we tried to figure out, well, where does the excitation go? And for that, so we're now here. Sorry, I should jump back one more time. We're now looking sort of here at the end of the simulation. Okay, sort of like where the proton is over here. And for that snapshot in the simulation, we now plot the occupation number of all the quantum orbitals as a function of energy. The band gap here is the white region. Everything at lower energy is valence states. Everything at higher regions, which is gray here, is conduction band states. Here's your defect level. Okay, after the proton moved through it, it's singly ionized. 1 electron is gone. That's what we see here in the occupation number. And then this analysis tells us where the electron went. It actually went into an excited state, 3-fold degenerate, and all of these 3 states are sort of like excited states of the defect, as we see again from these partial charge density plots here. So in other words, what happened is the proton comes and excites the defect, and the defect is in an excited state. And so the question that we then asked is, how does that affect the motion of this defect itself? Like what does the oxygen vacancy do as a result of this being in this electronic excited state? The lifetime of the defect is long in magnesium oxide, on the order of nanoseconds experimentally. We unfortunately can currently not predict it. But what we then did is we looked at the diffusion barrier of this oxygen vacancy for different situations of the electronic system. So the black curve is the ground state. And if we want, and we use this transition state theory approach here, where the defect diffuses from this position here over to the corner of the cell, which is actually symmetry equivalent to the starting point, but anyway. And then we look at how large is this barrier in the ground state. Okay, ground state is maybe 4.5 electron volt or 4.3. And then how much does this barrier change if the defect is excited? And so in this case, if we impose these occupation numbers that we got from our time-dependent DFT simulation, in the transition state theory, we see the barrier drops by about 0.94 electron volt. So that's a tremendous drop, especially given the fact that diffusivity in this material, or diffusivity of these oxygen vacancies, is determined by this exponential law here, right? By this Arrhenius law. So this barrier enters in the exponential, so a 1 eV drop is big. So in other words, this electronic excitation can increase the diffusivity. We can play some number games by making assumptions here for the temperature and for, we know the geometry of the material. And so just to give you one example, at 900 Kelvin in this material, diffusivity increases by about 10 to the power of 5. That depends, of course, on the proton flux and things like that. So we give in the paper some examples, but the point being here, this excited electron effect can increase diffusivity. And I think that this is a mechanism that we can exploit to make to engineer defects in the material, essentially. It's also very spatially localized. Again, I don't have to discuss this maybe in detail. What I want to show you is two things. The first thing is, if you're concerned about proton beams, I agree, that is a concern. And so one thing that we tried to compare to is an external electric field, or in other words, a laser beam. And in this case, I just show you, this plot you've already seen, so I just show you the comparison, what the occupation number distribution is if we excite with a laser beam. In this case, we used a frequency slightly above to be able to excite the defect transition, and intensity like this one. And you can see that we see similar effects, right? The defect gets depopulated and the excited state gets populated. So I think this is actually doable also with the laser excitation, and that makes us optimistic that we can maybe use it for modifying materials. There are other advantages and disadvantages of using laser beams versus ion beams in terms of, for instance, spatial precision and all these kind of things. That's a different question. I think I will not address that here. The second interesting development is related to two-dimensional materials. So I showed you in my motivation slide for this part of the talk that people use these ion beams, and also people use laser beams to modify or to create defects in two-dimensional materials. And so we did two things, I would say. One is we looked at how proton beams affect very thin pieces of aluminum. So that seems artificial, and you probably tell me, okay, aluminum is not a 2D material. I agree. The reason we used aluminum is we had very reliable bulk data, and the interesting result was actually that for very thin aluminum, we believe that we see the effect of surface plasmons created by the incoming excitation on the energy loss that the projectile experiences as it moves through the material. And then the second example that we're looking at currently, this comes partly from a collaboration with the International Atomic Energy Agency, and it also comes partly from a collaboration with the SFB in Duisburg over the summer. We're currently looking at graphene under proton irradiation. We looked at the energy deposition in the material that is sort of published. I want to show you the currently recent interesting preliminary data we found, which is the pulse length and pulse shape of a secondary electron pulse that you get when you shoot the proton through the material. We can compute that now after we implemented absorbing boundary conditions in our TD-DFT code, and we see that the entrance side and the exit side show actually a different dependence of the secondary electron pulse shape on velocity. So these letters here indicate different trajectories that we shot the proton through the graphene. The numbers behind them are velocities. You can see it's preliminary data because it's not polished yet, but the numbers are at velocities of the proton in atomic units of velocity. And you can see that, for instance, let's say we look at the A trajectory on the left-hand side. In this case, the pulse becomes stronger as we go down in velocity, and this trend is exactly reversed on the exit side. So we're currently trying to understand those kind of trends. Motivation being that the SFB in Duisburg has a pump probe setup where the pump pulse is a proton beam and the probe pulse is then, for instance, a laser, and they want to understand these pulse shapes and this kind of thing. So that's actually very highly precise. You can see the time scale. These are femtosecond results. That's exciting data, and we want to compare that to experiment to the extent possible. Before I tell you a little bit where I see all of this going, I want to show you one last example of work that we've started in my group maybe now 3 years ago or 4 years ago, which is we are understanding excited states in antiferromagnetic metals specifically. The example you see here is manganese platinum. And in this case, we largely restrict ourselves, because the material is a metal, we largely restrict ourselves to density functional theory type of calculations. But the challenge comes in from a different angle, which is energy scales in these antiferromagnets are always tiny. Okay, so look at this, micro electron volt. That's difficult for those first principles approaches, and then there are actual ways that they're done with with a fixed charge density just to achieve this micro electron volt energy scale. But anyway, what we looked at in this material is, for instance, the magnetocrystalline anisotropy energy. So that's the energy that it takes to reorient the Neal vector in this material, simply because this barrier determines whether this material can be used efficiently for data storage, right? If you want to switch the Neal vector somehow, that may be a different question how you switch it experimentally, but if you want to switch it, the barrier cannot be too high. At the same time, if you want to store data, the barrier can also not be too low. Anyway, the theoretically interesting result from our current point of view is that when you look at this magnetocrystalline anisotropy energy, people typically come from ferromagnets when they study this, and they look at this contribution from the spin orbit interaction and exchange interaction. So that's the black curve. In these antiferromagnets, simply because of the energy scale of this, there's also a magnetic dipole contribution that needs to be accounted for. So that's something that Kisung in this case implemented, and for magnesium platinum, we're about to submit this, and for a couple of other antiferromagnets, we have a paper in the archive. We also can use these techniques to study electron dispersion, phonon dispersion, and magnon dispersion, and by doing so, we can disentangle those individual contributions to the heat capacity of electrons, phonons, and magnons. And so in this case, for instance, we found that in this material, simply because of how these dispersions work out, the phonon contribution is the dominant term at low temperature. Magnons don't actually dominate there. And we also derived an approach to calculate the susceptibility of the material. One last interesting thing, because we talked about optics a lot, is shown on the right-hand side, where we calculate the Kerr rotation of the magneto-optical Kerr effect of this material. But because we have access to the individual states that contribute, we can tell for each peak in this case, spectral dependence here on the energy dependence, we can tell where each peak comes from. So all these transitions into manganese states or into platinum states, what dominates more in what energy range, and so on. So I think this provides us a very detailed insight into the magnetic structure and magnetic, magneto-optical properties of this material. All right. So in the last couple of minutes, I think I have maybe 5 minutes left if I did look this up correctly. I want to show you a little bit of where we see this going. Like, what are we going to do? Where do we see the challenges that need to be tackled? So the first one, and I want to start with that because I think that's the one where we're maybe closest to coming up with a solution, not a solution maybe, but with interesting data comparable to experiment, is we want to use this excited electronic state and exploit it to tweak defects in the material, potentially for qubits, but again, that doesn't matter so much for our case. The qubit analogy comes simply from the fact that the way you make NV centers in diamond, one of the ways is to ion bombard the material. And I think that this excited electronic contribution to diffusion can be exploited for that. So we're just currently investigating some ways to look at how we can make that diffusion directed, for instance, because it's not enough to just get large diffusion of defects. You kind of want to get them in or out of the material, and for that you need to direct the diffusion. So we're trying to figure out how to do that. In this case, you see time-resolved data where we bombard a 2D material. This is graphene again, with silicon of different charge states, and you can see how the following dynamics really depends completely on how highly charged the impact silicon was, right? If it's very weakly charged, the excitation disperses essentially completely, whereas if it's highly charged, the excitation remains, and it remains actually relatively localized. So those things affect the ways to use this effect to create defects in the material and to understand how, what defect you create maybe and how fast it diffuses and so on. So one of the limitations we need to overcome for magnesium oxide is that the diffusion barrier in the ground state of 4.3 electron volt is of course massive, and so seeing that effect directly in experiment is maybe not so good for magnesium oxide. So we're currently looking at that. But we hope that this gives us high precision to tune defect properties and also high defect specificity simply because we trigger specific energy transitions. In the context of quantum computing, I don't know if you may not have seen this in the news. It was sort of a big article here. There is a quantum an institute that works now with IBM here on campus that is about to start, and we hope that we can use through that collaboration potentially that we could maybe use some of these quantum embedding techniques to use IBM's quantum computers to supplement certain parts of first principles calculations with quantum computing. So there are examples by Ivano Tavernelli, for instance, in the literature, and Giulia Galli that have used some of these quantum embedding techniques where you wouldn't run the entire thing on a quantum computer, obviously, but you can use this quantum embedding technique to maybe focus on a certain defect and things like that. So I think that is promising. I think this, either making qubits or using qubits, I think is both a promising direction in the field that we should and hopefully can explore in the future. The Second example goes back to the excited state dynamics that I discussed earlier. So where I said, okay, we would like to predict the temperature over which the electrons thermalize, for instance, or the time scale of this thermalization process, and maybe the importance of electron and electron phonon scattering. So currently we cannot do that, but Keesong found, this is a preliminary data, so please don't scoop us. Keesong found an interesting effect here in ferromagnetic iron, where both a lattice temperature, so in other words phonons, or a magnetic temperature going away from zero, both really change your dielectric function, or in other words, the optical properties of the material. The contribution you see here is without the Drude model, but which may matter for iron, but the effect is a strong influence on this dielectric function through magnetic temperature as well as lattice temperature. And I think that is really a promising direction to study. So we trace this back to breaking the symmetry essentially, so making, otherwise dipole forbidden transition dipole allowed, weak but dipole allowed, and that leads to these changes here, both for phonons and for magnons. But I think the impact and also the implications are broader than just that. I think this could affect excitons and things like that. We just started looking at that. Explicitly, I mentioned this earlier, we want to predict the time dynamics of these equilibration processes, either through improvements through time-dependent DFT, or maybe by coupling it to approaches like the Boltzmann transport equation. And we want to connect that back to the screening, right? So again, if you do this in a doped material versus a non-doped material, the screening changes, as I told you earlier, and that will impact this equilibration dynamics, because the screening changes the electron-electron interaction. Magneto-optical effects. So this goes back to looking at something like this, but for the off-diagonal elements of the dielectric tensor, that would give us magneto-optics, and those are examples of what we want to study. And the last one, this is the one my group has the least experience with, but we're exploring it to some extent. So I have currently maybe one student looking at this, is how can we use databases and incorporate that into our research. So currently we're looking at two examples. One is we want to use these machine learning techniques of optical spectra. So it is still related to excitations, but of optical spectra to maybe improve predictions using cluster expansions for alloy systems. So this is super early preliminary data, right? So I cannot even tell you the full story yet because this is a moving target. But we would like to work to some extent and see if we can identify problems in the excited state realm where these machine learning techniques can help us, or alternatively where databases can help us, existing databases. So Ethan Shapira, he's a student, he's about to graduate, and he started looking at plasmonic materials. Okay, so I think that is where I will stop here. I have one slide of conclusions. I'll keep it general, and then I'm happy to take questions. So I hope my talk convinced you that predictive materials design, which is the topic of this workshop, certainly has challenges, right? So usually we struggle with balancing accuracy versus computational cost versus the parameter space that we want to explore, right? Materials parameter space, for instance. There are multi-scale problems, and then there are issues of running any of these simulations really on modern supercomputers, because that hardware also keeps changing, right? So you may have to adopt to GPUs, and who knows, maybe quantum computing in the future. So exploiting that requires work. At the same time, I think there is certainly promise out there, right? So these excited state effects are experimentally accessible, their dynamics is experimentally accessible, and I think they have actually an impact on what you see in experiment. We have techniques that work relatively well, other techniques may need more improvement, but I think that is certainly interesting and exciting to work on. And of course, we want to connect this to experiment whenever possible, because those predictions ideally are, we've seen it from the previous speakers, ideally are comparable to experiment, certainly qualitatively, ideally quantitatively to, limitations that depend on the system, but we do want to connect this to experiment wherever possible. Okay, I thank you so much for your attention. Thanks for bearing with me for this long, and I'm happy to take any questions that you guys have.
Thank you. Yeah, thank you for the very exciting and energetic talk. Are there any questions?
By the way, I don't see the chat, so if you speak up, I think that's easier.
Let me see. Oh, there's no questions in the chat, but
okay, good.
I will start with a question myself.
Yeah.
So, for your first part of the talk with the study of these sort of ultra fast or the dynamic response. I find that very interesting because most of the studies of optical properties I've seen usually doesn't really take into dynamics very well. But you focused a lot on absorption. How about other nonlinear effects such as the, let's say, second harmonic generation, electro-optic effect?
Excellent question. So, okay, what I can say to that is we have not simulated any nonlinear optics in my group. That being said, that is one of the directions we did start discussing over the summer, also with Duisburg, because they do they measure some nonlinear optical properties. So there are approaches in the literature that can use either DFT or even the Bethe-Salpeter approach and look at things like second harmonic generation. Currently, we don't have that implemented, but it's certainly something we played around with thinking about at least, right? So I can't show you any results, or I can't show you maybe what the real limitations there are. I do think it's possible in the first principles context. We may have to look at how we implement it, but I think it's interesting and there is potential there. Certainly that is accessed in experiment as well. So I think that would be a nice thing to look at.
Okay, so that's interesting. And then I'll save my second question later. I'll pass this through. Oh, okay. Then I have another question. I didn't understand what quantum embedding was. You say IBM, yeah, like what is quantum embedding?
Right. So I think the way to look at this, without us having done any of the simulations, so this is super early. This institute is, I think, not even officially started yet. It's in the evolving process. But the paper that you can find in the literature, for instance, Giulia Galli's work, what they're essentially doing is they're focusing on a defect in the semiconductor, let's say. The semiconductor can be described by DFT on a classical computer, and then that provides input for the quantum Hamiltonian of the defect states, and you can then obtain insight into the defect states, and that sort of like smaller problem parameterized by DFT, that's where the embedding comes from. It's sort of like this defect is embedded in a bigger piece of material, let's say. That is what then is run on the actual quantum computer. But again, I just want to be clear, we have not done these simulations. Okay, this is something that we hope to be able to explore once this work with IBM starts to gear up.
Okay. We'll pass to Stuart. I think he has questions.
Oh yeah, I had a question. Thank you very much for your very nice talk about the antiferromagnetic metals that you discussed in 2 parts in your talk. And the first question would be, you showed Kerr data, energy dependence of the Kerr signal for manganese 310, which is a chiral antiferromagnet. But my understanding was that the Kerr signal is extremely anisotropic. And I just wondered what you actually were presenting.
So this, I think, so I don't think we looked at the anisotropy for this material. I'm trying to jump back to this one. Is I think the slide that you're referring to, right?
That material it's of course known that the properties are determined by the Weyl points. It's a Weyl semi-metal, and it has this enormous Hall effect, which is highly anisotropic, as is the Kerr signal. And I just wondered if what is that Kerr rotation corresponds to which orientation?
Which orientation? I'd have to look back at the paper actually. I think in this case we reported one orientation in the material, and that is in the paper, but I cannot remember off the top of my head.
It depends very much on whether the light is propagating perpendicular or parallel.
Right. So that we have access to this information through the dielectric tensor. So the way we compute this, I can tell you that at least, is we calculate the full dielectric tensor, so all diagonal as well as off-diagonal components, and then that relative to the orientation of your field tells you about the anisotropy. Okay, so yeah, even if it's not in this figure, we do have access to that data.
Fantastic. My question really was, is it possible to use these magneto-optic properties to determine the chiral structure? You're showing two different...
yeah, that's a good question.
Very difficult to determine in thin films, as you know, antiferromagnetic structures, even with neutron scattering. That was one. Anyway, I got the point. Second question was, you talked about manganese platinum, and I didn't understand this anisotropy because manganese platinum is a collinear antiferromagnet, but my recollection is that the moments are aligned in the 1-1-1 plane, and therefore there should be a six-fold anisotropy, where you showed a two-fold anisotropy. So what were you actually presenting?
No, so yes, so the magnetic moments, they are in plane, and then if you rotate them, so what we simply did here is we rotate the Néel vector in our simulation, and we calculate how that changes the total energy.
Maybe I'm wrong. Recollection is the moments in manganese platinum, which is FCC, lie in
Yeah,
a
yes.
should be a 6-fold anisotropy axis. You appear to show a 2-fold anisotropy. How is that?
Right. So we certainly didn't see a 6-fold anisotropy, but I'm happy to look at that with you if you find that it to be 6-fold. It is a cubic material, that's for sure.
Thank you very much.
Thanks.
Yeah, I can take the opportunity to ask one more question.
Yeah.
I think we have a few minutes, right? The next one is 5 minutes away. So then I have one other very, kind of burning question. It was sort of towards the end also when you talked about, I think, trying to use these, you're trying to do quantum computing, use your technique to advance quantum computing. And I didn't quite understand, you wanted to use a quantum computer to do simulation, but it's really to try to understand how defects diffuse in the silicon to make a qubit. Is that sort of the idea?
I don't. Do you still see my screen or not?
No.
Okay. All right. Then maybe if you want me to share again, I can. I can also just explain it like this. These were two different things. So what we would like to do is we would like to precisely control the defect properties in a material in order to make defects that can be used, for instance, as single photon emitters or as qubits. So that is part one, right? That is not using any quantum computer. That would be going to the to excited state dynamics and using that effect to manipulate position of defects, maybe distances between defects, and things like that in a material. The application of the quantum computer, that is something future work, right? So that, again, we haven't done those simulations, but that is something we would like to explore to the extent where those quantum computers can help to overcome accuracy limitations that we have in the first principles techniques. So it's not, these, you should really view this as two separate aspects.
Okay, got it. Okay, and then so at UIUC there you have a quantum computer, or
that would be awesome. I don't have a quantum computer here, but like I said, this would be work that this institute with IBM is about to form, and so I think that's where we would hope to get access to those kind of resources.
Okay. Oh, that's very good. So.
But by the way, so some of that is actually already accessible online, right? If you go to so IBM has tutorials and things like that certainly simulate running on a quantum computer. And I believe that you can also apply it for time there and try that out and this kind of thing. We would just like to build this into some more than that exploratory work.
Okay, and would a small number of qubits be enough to do calculations, do you think? Like, I've never,
Excellent. I think, so, the way it is, people simulate what they can on the amount of qubits they have, I would say, right? So I think in general, it's of course true, the more the better, but that's also very challenging. And so I think that is why these quantum embedding techniques are helpful, so that you don't have to simulate the entire thing on the quantum computer, but just you use DFT maybe for parts that DFT is relatively suitable for, and then the quantum embedding technique only treats the subset of your system that is maybe a bit more tricky. And for that, so like I said, if you look at the literature that exists there, like for instance, I want to point again to Julia and Ivano's work, they use those available numbers of qubits for these results.
Okay. Oh, very interesting.
Yeah, I think so too. Like I said, we don't have much experience in it, but I think it's a promising direction.
Okay, great. Thank you. Yeah, thanks so much, André.
Thank you.
With that, then I pass to